Hello, hello, hello. Good morning, everyone. I know some folks are still grabbing a bite to eat and get some coffee. That's totally fine. We're just going to get things rolling this morning. Welcome to Clean Lakes 101 Science Cafe. I'm Dana Bolton, a morning meteorologist at WKOW. Our station is a proud media sponsor of these events. So I want to welcome everyone this morning for enjoying the sunshine today and joining us in person, as well as those folks at home that are joining us virtually via the Zoom webinar. Today's Clean Lakes 101 is all about PFAS, what it is, where it comes from, how it gets into our water, and how it impacts the organisms in our beautiful lakes. We will have time for a Q&A session at the end. So just a reminder, if you are joining us virtually, be sure to utilize the Q&A function on your screen, and we will get to as many of you as possible before the end of the presentation. And as always, if we don't get to all of the questions, we can email them in afterwards and get things answered for you. Before we start today's talk, I want to introduce Terry Gorski, the National Guard Life Insurance Company, to tell us a little bit more about today's event sponsors and speaker.
Thanks, Dana. Thanks to everyone who's joining us here at the Edgewater today, as well as those of you online. I'd like to start by thanking the sponsors of our Clean Lakes Alliance 101 Science Cafe series. Presenting sponsor, National Guardian Life Insurance Company. Hosting sponsor, the Edgewater. Supporting sponsors, Johnson Financial Group, Alliant Energy, Perkins Coie, and Hubdy Properties. Production sponsors, the UW Nelson Institute for Environmental Studies and the UW Extension. And as Dana said, we're happy to have WKOW as a media sponsor. For 115 years, National Guardian Life Insurance Company has been a trusted member of this great Madison community. It's an honor for us to invest in crucial initiatives and to give back to help make our community a better place. On behalf of everyone at National Guardian Life Insurance Company, thank you to Clean Lakes Alliance and each of you here today for everything you're doing to ensure we have a clean, healthy water resource available. A few quick announcements. Next month, Clean Lakes Alliance is a special contributor to Downtown Madison Incorporated's September What's Up Downtown presentation. Join us on Wednesday, September 25th, back here at the Edgewater for a special presentation on the recently approved master plan for the Lake Monona waterfront redesign from Olin Park to Machinery Row along John Nolan Drive. And of course, Sasaki's principal lead for the project will cover key design elements that will positively impact water quality, including innovative stormwater runoff treatments. Registration information can be found on Downtown Madison Incorporated or Clean Lakes Alliance's website. Clean Lakes Alliance has several upcoming volunteer opportunities. Tomorrow, Thursday, August 15th, Clean Lakes is partnering with City of Madison Parks to remove invasive species and litter at Cherokee Marsh. Get your hands dirty to make our lakes cleaner. And mark your calendar for Tuesday, September 10th for a seed collection event at Holy Wisdom Monastery from 4:15 to 5:45 p.m. It's a great way to get involved to make a positive difference for our lakes. Email Caitlin at cleanlakesalliance.org to learn more and sign up. Back to today's talk. Today, we're joined by Patrick Gorski, an emerging contaminant research scientist with the Wisconsin Department of Natural Resources. Patrick joined the DNR in April 2020 to research PFAS in surface water, fish tissue, and other aquatic organisms. He received his PhD from UW-Madison, studying mercury bioavailability and bioaccumulation in freshwater systems, and obtained his master's from UW-Madison Zoology Department. Here today to share more about the PFAS in our local chain of lakes, please welcome Patrick to the stage.
Great, thank you for the introduction. I appreciate you inviting me to talk today. A couple of the goals of, actually before I move forward, since it's up there. So I'm in the Bureau of Water Quality. So water quality means surface water. which is rivers, lakes, and streams. So I'm gonna mainly be talking about surface water here as opposed to drinking water. That's another bureau at the DNR, so I'm gonna be mainly focusing on that. If you ask some questions about drinking water, I can try to be dangerous and answer some of those, but I'm gonna focus on surface water today. And I have a few goals for the talk today. Hopefully I can give you a working knowledge of what are PFAS. I know a lot of people, once you see that acronym, your eyes glaze over and you stop listening. So I want to give you a working knowledge, so hopefully you can walk away and kind of understand what are PFAS, what are these different chemicals, what's that gobbledygook that, you know, that they have on my drinking water analysis that I'm looking at. What concentration should I be aware of? You know, what are some benchmarks? So hopefully I can hone in on that. So I also want to give you the idea of concentrations, and also those concentrations, put them in perspective of what we're seeing across the state. So I'm going to give you a statewide view of what we've been doing, and then put the Yahara Madison Lakes in that overall perspective and give you a feel there. Also, I've been doing research on the Madison Lake, specifically Lake Monona. So I'm going to talk about a little bit of the research there and give you some real world data to look at. So I'm not going to shy away from getting too glossed over. We're going to jump right into the details. Also, what I've known or what I've experienced is you can't cover PFAS in a simple soundbite, you know, in a tweet or something like that. You have to kind of get into the meat of it. So hopefully I can give you that understanding of after this. So hopefully this works. I've done this before, but anyway, so I'm going to talk about, this is my PFAS primer slide about what are exactly PFAS. So PFAS are per and polyfluorinated alkyl substances. That's what the PFAS stands for, and it's a plural term. They're a man-made organic compound. There's thousands of them right now. At the state lab of hygiene, which we often send our samples to, we only analyze for about 33. I'll talk about them more in depth later. And these were developed in the 1940s. This is kind of an outgrowth of actually building of the atomic bomb and so forth. So these are man-made chemicals. They didn't exist, you know, pre-1940s, so we've only seen them since World War II. And they're not, and once again, they're not naturally occurring. The basic structure of them is that there's a carbon chain and it's attached with fluorine. So you have the C and the F. And that bond between the chloride and the carbon and the fluorine is very difficult to break. It's one of the strongest bonds in chemistry. So that's what gives them the name, the forever chemical. That's really difficult to break, and they're doing a lot of research right now on how to possibly break that, but it doesn't naturally break down. And so you have this carbon chain, which is a tail, and then you have a functional group, which is a head. And that carbon chain can vary in length, 4 to 12 compounds or carbons. So, so there's a lot of each different length has a different name. Two of them that I'll focus on are one is called carboxylic acid. So carbon dioxide, or there's a carboxylate head, that functional group, and the one we're familiar with, or you often hear of, is PFOA. So, and it has 8 carbons, and then it has that CO2 head. The other one, and here's on the left side, here's a diagram of chemistry structure of it. So you can see on the far right side, your right side, is that CO2 group. If you put, instead of a carbon there, you put a sulfur group, you have a sulfonic acid. So it's a sulfate head. So, and the one we often talk about and hear about is PFAS, FOS, the S stands for sulfur. So these are the two that we often hear about. There's the most toxicity data existing for PFOA and PFAS, and we have surface water standards for these in our state. The reason why we focus on those two is it takes a lot of time, effort, and research to build up the background to know what are the toxic levels that we should look at and what they do to the human body and organisms and so forth. And one of the main things that they has found in humans is they cause cancer, reproductive effects, and hormonal issues with people. So they're very, it's not good to be ingesting these at high levels. Also PFAS, FOS is the form that bioaccumulates. A lot of the other compounds we've measured in fish and other organisms, we often don't see them. PFOS is the one that will be going up the food chain, so that's why we'll be talking about that. So PFAS and PFOA. So that weird structure of it imparts valuable chemical properties, and that's why it's been used by the chemistry industry and got really prevalent, and it's everywhere right now because it's this really really valuable in the fact that it can form a boundary between air and water, between that functional group and that carbon tail. They basically can form a film, and they can, like, they're often considered a surfactant, much like soap. And they're excellent, and this is the most important thing for industry often, is they're excellent at water and oil repelling properties. And they're widespread in a whole lot of different applications in industry. So I threw together some pictures here of what they can be used for. Often, you've heard of Scotchgard, and we've put Scotchgard on a lot of different products because it can repel water, or if you spill your wine on your carpet, that's really valuable. Another really common use is Teflon, non-stick coating on pans and pots. Also non-stick coating on wrappers for food products, such as, you know, your hamburger wrappers and so forth, pizza boxes. This is getting less and less prevalent because people have known that this happens. But instead, often back in the day, they used wax, but now they started to switch over to use PFAS, and unfortunately that can get in your food. Chrome plating and metal plating is another source or use of PFAS. Often it's used in mist to suppress the when you're plating the metal. Personal care products, I just put a couple on there as representative, and dental floss. Let's say lipstick or sunscreen or some of the other things that you may be using for personal care. Also, any other coating that you can think of, electronic wear or electronics, paint. Also on, let's say here, I have the barrels here, but not the barrels themselves, but the coating of the barrels to avoid the metal from rusting when you're using caustic material, let's say acid or some other really nasty chemical, you could coat the inside with PFAS and repel that. Also back in the day, I remember, I don't know, maybe I'm showing my age, but the greatest fear was people to fall asleep while you're smoking a cigarette on your couch and you set it on fire, right? Maybe that's not the concern anymore, but there was a lot of, you know, studies on looking at flammability or reducing the flammability of any of your, let's say your sofa, any of the things in your house, or let's say the curtains. So that was often coated with PFAS because it will reduce the flammability. And also another major use that we found for PFAS is that it can be used in firefighting foams. You may have heard of AFFF, and I'll talk about AFFF. That's aqueous film forming foam, and that's used to smother fires. So when you have a really bad fire, you can use PFAS to extinguish it because it's basically like a liquid blanket, and it'll cover the fire and smother it. So if you have something, let's say like airplane fuel or something that would burn readily and for a long time, it's advantageous to have something like this. I mean, I think we all probably seen what happened with 9/11. You can appreciate how explosive and incendiary airplane fuel is. So it's used in firefighting foam. One thing I'm gonna be talking, as I said, about surface water, and I'm not gonna be telling you anything that you can't find yourself. So this is all public knowledge, actually. So if you go to our website at the GNR and you Google, or you DuckDuckGo, I should say, whatever you want to use, Wisconsin GNR PFAS, you get to this page on the right, or you get to the PFAS page on the right side of the page. You can click on the viewer and you can see our website, and you can click on and off the different layers if you want to look at the fish let's say, the brown areas are for fish consumption advisory, there's investigation areas, square. Surface water are the diamonds, the blue and pink diamonds, that's what I'm gonna be talking about. And you can see these different areas, so I'm gonna be actually just showing you the numbers. If you click on those, let's say those pink diamonds, you can actually see the concentrations as well. So that's something that we're working on, and basically, most of the data is I'm showing that. So the things to consider about PFAS, I'd like to talk about this, I've added this slide. So when sampling for PFAS, there's a good chance you'll find something. Part of the reason that you've been hearing about it is that we have very sophisticated and sensitive analytical methods the past couple decades. We have mass spec detectors, which are very sensitive, and they're actually measuring the atomic weight of the molecule. So you can start, we now know that we can, we've developed those methods, standardized them, so you actually will detect PFAS. But the devil's in the details. Like I said, sensitive analytical methods. Detection does not necessarily equal contamination. Because we're using these very sensitive methods, will often detect everything. And if you see a news bite or something, they'll say, PFAS was detected here. Your next question should be, well, which PFAS? PFAS, there's thousands of them. Can you tell me which specific compound? Because some have lower toxicity than the others, let's say like PFOA or PFAS. And what concentration is it? Does it rise to the level which I should be concerned? So you need to know the compounds and the concentrations to determine the risk. Should I be worried about this? So which PFAS are we talking about? And you need to compare this to the standardized concentrations. So that's what I'm going to get into next, is talking about, I'm going to mainly focus on PFAS and PFOA, but put this concentrations in perspective for you. So what I did for this part of the talk is I showed you that surface water data viewer. I pulled all the samples from that. Actually, we have more recent samples, but this was done a couple months ago. It doesn't look like much, but there's a lot of clumping down in that lower left area. And I have the PFOA concentrations on the left and the PFAS on the bottom. And pay attention to the axes and the concentrations as I talk. I'll point that out, but I thought I should mention it. So I pulled all that and put it on here. And then we have sampled over 300 sites now in the state of Wisconsin. So this is everything. And by the way, sometimes I forget to mention, a PFAS sample costs about $500. Some people don't realize that, but in real world kind of things. But we have two types of areas that we sample, and that affects the data set. So what we do is we do background monitoring to just see what's out there. Because when we first, several years ago, it's like, okay, yeah, we're going to detect something, but should we be worried about it? So let's look at everything in the state. And then when we found some high numbers, we have targeted follow-up. So that's what the red are, these targeted follow-ups. So those are a little oversampled. So some of those sites in the state are overrepresented because we'll find a hotspot. And then we go around and try to find out how far away, we have contamination and so forth. And then we have the background monitoring. So we have the red and the blue happening here. And as you see, there's two outliers or very influential data sets. There's one really high in PFOA and one really high in PFAS. And one is Snowden Lake, which is up near Rhinelander, and the one on the bottom is Starkweather Creek, right down the road from us. And that's the sample over at Anderson Street. Anderson Street is the crossing just south of the airport. You've probably driven by it on the way to the airport or maybe MATC. But that's that sample. So now on the left side here, what I've done is I've removed those 2 points because they're very influential and you have that big clumpy. So I got rid of Snowden Lake and Starkweather, and you can start to see the spread of the data, and you can see that some of the data is, spreading out across that PFAS concentration on the bottom, and some is spreading out across the PFOA. As you can see, the scale went down a little bit by over half. But what are those sites? Well, let's drill down and look more at those sites. Is there something distinguishing, or is that just general scatter? So on this graph, what I've done is I've peeled away, instead of the targeted, I've actually given you what those sites are. So as you can see on the pink or the purple on the left side of the graph is that area which is around Stella. Stella is the area east of Rhinelander around Snowden Lake. So all those are within the watershed of the Stella area. And then on the bottom, that's all Starkweather Creek. And actually, if you look at Starkweather Creek, that's, going from the airport, and as you get farther from the airport, it gets less and less. And this is the west branch of Starkweather going up to the airport, not the other branch that goes towards the Beltline or the highway. We have some other areas. There's the rest of the Yahara chain, Mississippi, La Crosse River watershed, another area that has high PFAS, if you're familiar with French Island and what's going on there. So on this next graph, I took out Stella, I took out Starkweather. And what you see is the Yahara chain, which is the light green on the bottom. And then you have the Wisconsin River, which is the black, which is high in PFOA. So this is in doing this sort of reduction in going through these different sites. And also you can see that on the right side, the scale is going down. But what's happening here is actually the difference in, or the flow of the watershed. So like that Stella area, Lake Snowden flows into the Stella chain. There's the Moen chain of lakes. The Moen chain of lakes goes into Pelican River, which flows into the Wisconsin River and keeps going down. So what we're looking at is the flow of PFAS, and as it goes farther from the source, the concentration decreases. Also from Starkweather, it goes farther down through the Yahara chain. I'll show you more numbers there. And keeps going downstream. The La Crosse River watershed, you can see in there, is also high. So I'll talk a little bit more about that. The La Crosse River watershed flows from another airfield, out over north of La Crosse. Shoot, blanking the name right now. Anyway, so there is similar usage being on. Okay, so let's look at the background monitoring sites in comparison. So what we did for background monitoring is we have long-term trend river sites. So these are routinely sampled year after year, and these represent all the major watersheds in Wisconsin. So we added a PFAS sample. So the dark blue, sorry, is those long-term river sites. And I want to pay attention to I want to show you the, I won't go back, might screw things up, but yeah, as you can see, the numbers are basically below 10 on each axis, so these are very low concentrations. But those rivers are the dark blue, and then the light blue, we do an EPA-funded assessment of lakes on a regular basis. And then the light blue represent the lakes in the state. And these are all statistically sampled to represent an overall representative of your average lake. Let's say if you take a dark and throw it on a map, simplifying things, and you sample that area, this is what the concentration would be. So as you can see, these are all below the surface water standards, particularly the lakes. I'll tell you what the standards are. I just realized I didn't have that. But this is what we'd expect for most surface water of the state. They're very low. So you need to be near a source of PFAS contamination for it to be high. So your average lake or river in the state is going to be low, and you're going to have low concentrations. I thought I'd represent the data a little bit differently on this map. And I have a bar chart. So I have that Stella area, which is up near Rhinelander on the left, and then I have that Starkweather data right next to it. And as you can see, those are very high concentrations, triple digits. Interestingly, as you saw, Starkweather is higher in the red, the PFAS, Stella is higher in the blue, the PFOA. But then I took averages of these other areas. Oh, Fort McCoy is what I was blanking on. So Fort McCoy is upstream of the La Crosse River watershed. Fort McCoy, the water from Fort McCoy flows into the Silver River, which flows into the La Crosse River, which flows downstream. So that's at Silver Creek, which is at the outflow of Fort McCoy. So as you can see, the PFAS is also higher in Silver Creek. Lake Monona downstream, Wisconsin River, Mississippi River, those long-term trend rivers, those are all really low in comparison to these two others, especially Starkweather Creek. And interesting, the Menominee River, which is up near Marinette. And if you heard about JCI, Tyco, and so forth, the contamination up there, the groundwater is not flowing into the Menominee, interesting, it's flowing the other way, so actually, that's what's going on there, I thought I'd show that. So the highest in PFOA is Stella, highest PFAS Starkweather. So those fallout sites are intentionally oversampled, so they're overrepresented. And so, but those are very specific and not widespread, so you need to have that contamination in that area. On average, you're probably going to see a background concentration. People often ask me like, oh, I have a cabin up north on this lake. Is it going to be high? I'm like, well, do you have an airport nearby? And so forth. So rest assured that's probably going to be pretty low. So when we have these high concentration areas, we want to see how widespread the contamination is. So I'll give the example of the Madison Lakes here, since that's where we are. So the Clean Lakes laws. So this is some sampling that we did. And here are the concentrations. I forgot to have those on our earlier slide. The Wisconsin surface water standard for PFOA is 95 nanograms per liter, so that's way off the chart up there. But what's more relevant often for fish is the PFAS concentration. The surface water standard is 8. So I outlined where the 8 is there. And I put some other relative concentrations so to give you a perspective. So Devil's Lake is not part of the Madison chain, rest assured. But anyway, I want to give you an idea. We know Devil's Lake, there was no industry since 1940 or anything involved there. So even though nothing's, no industry by Devil's Lake, that's the kind of concentration. It's like 0.5 or lower. So that's what Devil's Lake looks like, and it's really similar to Lake Mendota. It's not until you get, so I have Lake Mendota, the Twenty Locks, the outflow to Monona, kind of over by like Willie Street and so forth. Lake Wingra, as you probably all know, is not actually part of the Madison chain, but I thought I'd put that on there. It's not until you get over to Lake Monona until you see this jump, and that's where Starkweather Creek comes in, as you know. Some of that water may be going into Monona Bay, but it's going all the way down to the Rock River, and you can see the elevated concentrations going down to the Rock River. Many of these are above 8, which is above the surface water standard. As you may know, there's fish consumption advisories. We followed up with the fish sampling on the Madison chain as well. Interesting, people always ask about wastewater treatment plants and so forth. As you can see, the Madison Met, we sampled that. We've also sampled other wastewater treatments, in case you're wondering. But the PFAS is not high in these areas. Interesting, often the PFOA is higher than PFAS. I can talk more about that. But those are also not part of the Yahara chain, but I just thought I'd show those concentrations in case you're interested. And I have a 4 circled on here because this is surface water, so don't get confused, but that's the new EPA drinking water limit that they've been talking about. So that's where 4 is, to give you an idea. Don't drink surface water, but anyway, I just want to give you an idea where that falls in with some of these concentrations. To drill down even more into the weeds, I said we're sampling like 30, we are sampling 33 compounds. And we have, I'm just talking about PFAS and PFOA, but I thought I'd show you the whole shooting match here, just to confuse you maybe, and plus they're really cool looking graphs. What we have here, so all the blue concentrations are the carboxylic acids. So you have, that's on the right side here. So, and I have them in increasing chain length. So PFBA is the light blue, so that's a 4 carbon. Oh. Oh, cool. Okay, so that's PFBA, and then I have the reds with PFAS. Oh, for some reason these got screwed. Anyway, but and increasing chain length. I guess these are correct, but that got switched on me. Okay, I'm getting confused. Sorry, these got a little confused. But anyway, it's pretty easy because you have the a way to remember this. You have B is the 4, 5 is the penta, like a pentagram. 6 is the hexa, hepta is 7. And then you have the octa, that's what the O stands for, it's 8 carbons. And then you get longer, and then you get up to 10, which is the deca, and then you have unideca, dodeca, trideca. It kind of makes sense, actually. So if you see an S at the end, that's a sulfur, and if you see an A, that's the carboxylic acid. Anyway, maybe you don't want to put it. But anyway, but when you put on these pretty pictures like that, you can see that some are dominated by the blues and some are dominated by the reds. And you have the different areas, and I just showed you the PFAS and PFOA earlier. This is, I'm drilling down the weeds, but this is what you can do with these data. It gets into like forensic, they call it forensic chemistry. Some people call it fingerprinting. I don't really like that term. But based on how these PFAS were manufactured, they have different relative amounts of these of the different compounds. And so you can kind of infer the different sources as well, because and then some have very specific compounds as well. But as you can see, the one side you have the Stella area in the Wisconsin River. We know the Stella flows into the Wisconsin River, so you can see it dominated by the PFOA. A place like Starkweather Creek and then also Silver Creek, those come from airports, so they're dominated by the PFOS, that red, and also PFHXS. Those are common for firefighting fumes. So you can see that those, we have two different sources going on here. And then you can see that Starkweather flows into the Yahara chain, and that relative composition doesn't change much. These are not concentrations, it's just the relative composition of these areas. And then Mississippi River is its whole different beast. But these are those background concentrations. And they're dominated by PFPA. And as I mentioned, PFPA is that very short chain 4-carbon compound, and that's the one that's been shown in rain. And it's very mobile, it gets around a lot in the atmosphere and so forth. So that's one thing, there's been news stories that came out, who found PFAS in rain? And it's like, okay, next question. Which PFAS and what's the concentration? So often it's the PFBA or some of these other compounds. These have a higher threshold of toxicity, so you can have a lot more PFBA before you have to worry about the risk associated with it. But these areas away from sources are dominated by these short chain, very mobile PFAS. So that's what I want you to show here. So I want to get into some research now, because I'm sure you're interested in that, because we want to, not just the concentrations, we have some very practical questions in water quality. I'm in the monitoring section, and we want to know, are we collecting PFAS samples correctly? Are we taking a representative sample? I don't know if anybody here are volunteers taking samples, but you want to have a representative sample of your sample site and representative of your area. So the main way of monitoring is we take surface water grabs, which are 6 inches below the surface. So you basically just take the bottle, you keep it capped, but you put it below the surface, and then you open it up underwater, you cap it underwater, and bring it back up. So that's how we take the sample. It's pretty easy, glove hands, and you have some other things going on. But does that vary with the depth in the water column? I'm sure you're familiar with lakes, and you know that things vary as you get deeper and so forth. So that's a question. The massive lakes are pretty deep, so if we're not representing them well, we need to figure that out. And then are we missing anything by analyzing for just total PFAS? I'll get into that, because we take that whole sample and then we just extract it. And as you know, there's algae in there, there's total dissolved solids, there's a lot of other stuff. So is that a good way to do it? So I'm working on the difference between dissolved or particulate, because that becomes important. I'm sure you're familiar with, this group works a lot with phosphorus. That it's really important if the phosphorus is bound to the particulates as it's settling out, or is it dissolved, and sometimes it's more bioavailable to the food chain and so forth. So it's a similar idea with PFAS here. So the Lake Monona study. So how is PFAS distributed? Like I said, we just are taking it from the surface water, and you're probably familiar with the lake diagram on the left. So at the top of on the left axis there is the surface of the lake. The bottom of the axis is the bottom of the lake. So you're looking at a vertical profile. But you can have the different layers like the epilimnion, hypolimnion. And you have the distinct, thermoclines and so forth. This one even has chemocline, which is pretty cool. But you can, at the bottom of the lake, you probably know you have funky chemistry going on, you have redox cycles, you have a buildup of phosphorus, you have manganese, you have, you know, dissolved total P down there and so forth. I won't get all of it. I know some of you know. You know, I give a talk in Madison, there's like about 5 PhDs in the audience, but anyway. Yeah, I know this. Anyway, so things vary with depth. Does PFAS? Let's sample it. So I basically blew the budget on to take remember $500 a sample. I got some EPA funding to do this. To take a profile of the lake all the way down to the bottom. So I did this on Lake Monona in August 4th, a couple years ago. And there's some of the parameters on here. So the lake was well stratified. So the blue is the temperature. And if you're not familiar with that, you know, the thermocline, if you've gone swimming in a lake and all of a sudden it's cold when you're done deep, that's what's going on. The lake stays pretty cold at the bottom, but the surface warms up and then you have that really sharp gradient. So the lake was still really well stratified. And then also at the bottom of the lake, when you have a productive lake, as you know, in Monona and Mendota, you have decomposition going on. So it's anoxic. There's no oxygen down there. And that's interesting too. So you have like that going on as well. At the top of the lake, we have the algae bloom, and there's also the TSS that may be total suspended solids, that may be the algae, that may not, but there's, you know, there's junk at the top, whereas the bottom there's not. But what we found out for PFOA and PFAS, the gray and the black, is it was not stratified. It was basically the same top to bottom. PFAS doesn't care. So I thought that was pretty interesting. So the bottom line here is that we, you know, by taking that surface water sample from 6-inch grab, I think we're pretty, you know, well representative. We don't need to go out. People are asking me, you know, lake associations, how could we monitor for PFAS? Do we need to do one of these all the time and spend thousands of dollars on this? I don't think so. I think by monitoring just that surface water grab, we're doing pretty well. I did note seasonal differences. I thought I'd throw in the pretty colors again. But what I did is there's a couple distinct categories here. So there's seasonally. So there's May, July, September, and December. We can now sample in December. So I wasn't busy the week of Christmas, sort of like, is the boat still? Have you winterized the boat? Let's go out and take a sample. So I did that. But also, if you look on the bottom, I have the grab sample, an epilumnion sample. We have this bottle that we take down, mid-epilumnetic and a mid-hypo. And then those bars are like those pie charts. And so that's the relative proportion of the different PFAS compounds. So the relative PFAS percent is on that side. And then the actual total PFAS, so that's if you sum up all these different compounds, that's what you get. So as you can see, that black line, it does increase in September, but it's lower in the beginning. What we're thinking is, what I've understood about a lot of the PFAS contamination is coming from groundwater. So if you remember, we had a drought. So we, like last year, or like this spring, we're not getting, as you know, we're getting a lot of rain this year. But in this type of, last year, we had a groundwater dominated system. So that was probably the most influence of what's going on. I'm just, you know, I'm kind of hand waving a little bit here. But also another takeaway is that you don't notice a difference between the top, middle, and bottom of the lake so much as opposed to the seasonality. And then once December rolled around, it went down. So we're seeing seasonal differences. So what about that filtered, unfiltered question? So as you know, if you take unfiltered sample, you have the algae, you have the particles in there. So is PFAS dissolved or is it bound to the particles? That's really important for bioaccumulation. Let's say if it's all in algae or if it's all in inorganic particles, maybe it's settling out. So is it that could determine if it's going into the food chain or not, or if it's settling out in, let's say, settling ponds or whatever, or is it dissolved and going down? So it's really important to know that partitioning if we're looking at transport of a compound through a system like we are in the Yahara chain. So I'm working with the state lab at hygiene on coming up with a filtration method. And here, what I want to show is the pink and the red. So the red is particle bound PFAS, and then the pink is dissolved PFAS. And this is just the relative percent of total of those two compounds. And I actually show the depth. It doesn't vary by depth, as you can see, but most of the PFAS, FOS, is in the dissolved phase. 80% of it is dissolved, only 20% is particulate. So it's actually staying in the dissolved, it's not in the particle. I mean, unlike, so let's say like phosphorus or some of these other things are really adherent to particles and they settle. That's why we have settling ponds and things like that. Most of this is dissolved, which is pretty cool, and it's fairly consistent with depth. I'm still working on the filtration method, but I think that's pretty interesting. So that 6-inch grab is a good way to sample. We see slight differences. Maybe we need to pay attention more if it's what it kind of depends how contamination is getting into the system. If it's groundwater dominated or if it's surface water runoff, that may be important. And it exists in this dissolved state, 80% dissolved, 20% bound. And I looked at other compounds and only PFOS, although it's 20% bound, the only compound that was bound was PFOS, which may be important for bioaccumulation and so forth. I haven't really dove into that, but maybe that may be part of the equation. Keep going here. So how did we get that surface water standard? A lot of people for PFOS. This is the data that our lead toxicologist was using, Megan Williams. And we had a whole bunch of background data for PFAS, FOS concentrations in fish and water from Minnesota and Wisconsin. So I have on the horizontal lines the different fish consumption advisories. These may be changing in the future, but this is where we are right now. Above 10 to 50 is 1 meal per week. 50 to 200 is 1 meal per month. Above 200 is do not eat. So you can follow those on the left side of the graph. If you see a surface water standard of 8, when you get above the water concentration, which is on the bottom, the fish concentrations on the left, once you get above 8 nanograms per liter, you have fish consumption advisory. So this is the one data set we can kind of hang our hat and predict something. So this is how that concentration was come up with. One thing that we have found is that it doesn't always, I came from studying mercury accumulation, and if you know anything about trophic levels, you have like the, you have the planktivorous fish or certain types of fish, and then you have the fish-eating fish like the muskies and the, the walleyes and the northern pike. Those top predators really have the high concentrations of mercury or PCBs, like when we hear about bald eagles and so forth. In the systems in Wisconsin, we don't see that. What I have here is the PFAS concentration on the left, and the different colors represent the different feeding regimes of the fish. So you have insectivores, omnivores, and on the right, you have top carnivores. And as you can see, it's kind of like, it's all in the noise. We're not seeing, muskies or walleyes with the top concentrations. Ironically, some of the fish that we see with the highest PFAS concentrations are bluegills, white crappie, white bass. It doesn't really follow. So we want to figure that out a little more. And what we did on Monona is we wanted to start sampling other biota. Here's some field pictures of us picking bugs. And then you have to get a lot of bugs for a sample and putting them in a test tube. I also looked at aquatic plants, macrophytes, Cladophora, which is an attached algae. And we got young of the year fish. So they were born that year. So these are not yet fish-eating fish. So I want to look at non-sport fish. Also, we looked at zooplankton and algae. Here's a field sample of that. It's really difficult to pick algae. So we used a sieve and we size fractionated them into the algae and the zooplankton by different micron meshes. So that's what we did that. Here's the aquatic plants for Monona and Mendota. Monona's in the red and Mendota's in the blue. And on the bottom of the graph on the far left is the Cladophora, which is the attached algae, but then I have duckweed. We sampled that because that's sitting on the surface film. It might have higher concentrations. I have coontail curly leaf noble. One thing to point out, notice that it's all detectable in Monona, in the red. Only one sample, or one species curly leaf was barely detectable in Mendota. So it's definitely detectable and at concentrations that are noticeable in Monona. And this is so I had this done on a dry weight basis. And part of the reason I did that, and I want to look at just those macrophytes, which I've circled. All those macrophytes are less than 20 nanograms per gram. Actually, they're like 9 if you take the average of that. So it's pretty low. The reason why it's below, I want to point out it's below 20. Sometimes those macrophytes are used for mulch and given away once they're harvested. So these are definitely below the biosolids land spreading interim concentrations that the state is established. So they're well below 20, they're around 9. So these have not, I mean, although detectable, they're not outrageously high that you should be concerned about. This is interesting about the plankton. I have the, again, red and blue, but the algae and the zooplankton, as you can see, the algae are lower. A lot of the PFAS, and this is just all PFAS. I can show you, if you don't want to see it. Okay, but so there's a seasonal difference, and it's mostly in the zooplankton. I also looked at macroinvertebrates. Here we have amphipods, mayflies, damselflies. Once again, detectable in Monona, not in Mendota. For some reason, the amphipods were the highest. I'm not quite sure of that. Or why? Actually, I thought the zebra mussels on the far side would be really high because they're sucking up a lot of water. They're filtering water. They're processing a lot of the PFAS water. They're actually fairly low. And beaches, for some reason, were higher. Also, these small fish, this was really interesting. So we have a couple different kinds of fish here. We have the young of the year bluegills and the bass, which they were born that spring, so we sampled them in the midsummer. But we also have fish in here that have lived their whole lives. These are like adults, like the Brooks silversides, golden shiners. These are adult fish. So interesting, those YOY largemouth bass are about 50 nanograms per gram, which is the 1 meal per month fish advice. Not that you go out and eat young of the year bass that are like this little big, they're tiny, but it's really interesting that within under a year, they've accumulated that much PFAS in them to reach that level. So they're at a level of most adults fish in Monona are at that 1 meal per month category. So they already accumulate that much PFAS in their system. So some conclusions, Monona higher than I should say Mendota. Monona elevated compared to Mendota, sorry. Aquatic plants higher in Monona, and the zooplankton. I haven't really looked into why certain organisms are higher than the others, but now we have, this is the first data set that I've seen. Not a lot of people are looking at the lower levels of the food chain, but I thought that's interesting that the PFAS is really high in young of the year fish. So looking forward, here's some ideas for you to throw out. So Starkweather Creek continues to deliver high PFAS water to Monona. The graph on the left, as I mentioned, I've been sampling. So Monona is the orange, Starkweather Creek is the yellow. I've been sampling that at Atwood Avenue under the bridge. I'm not going to go, I could sample it all the way up at the airport, but I think that's a good surrogate to show that Starkweather is still really high, 10 times higher, and it's continuing to do this. That sample on the far right is May. I sampled in July, and I'm going to sample next month as well. But it continues to be ever elevated. One thing I'd throw out here, I think Starkweather Creek is sort of the orphan child of the as far as monitoring, as far as the Yahara lakes. There's no gauging station. I want to figure out loading. We can figure out how much mass and so forth is coming in, but there's no USGS gauge on Starkweather right now. There was one for a little bit. I've been talking to the USGS about that, but we know loading, if you're familiar with phosphorus from Pheasant Branch and all the other chains, but we don't know. I mean, Starkweather is not necessarily phosphorus. There's things, chemicals and things you can't see, and we really haven't looked at stark weather a lot. Monona continues to have high concentrations, and they still have the advisory. One thing, if you're still familiar with Dick Lathrop, I've been talking to him, and I asked him, what's the residence time of water in Monona? And he said 0.767 years. He has the data on this. What this means is that the water turns over or replenishes 1.5 times per year. So it's flushed out 1.5 times per year. Now, let's say if most of the PFAS is dissolved rather than bound to particles and not settling, it should flow through the system in 1.5 years. So theoretically, if we stop, I got this from Dick Lathrop, he talks about just with phosphorus, it takes less than 1 year for the PFAS to flush out of the lake, because it's dissolved. And we know it's not settling down, so it may not be coming back up from the sediments either. And I've seen some talks and unpublished studies that fish respond pretty quickly to reductions in PFOS concentrations, like 2 to 3 years, to reduce their PFOS concentrations. So can we stop it from entering? Potentially, yes. There are approaches that can be discussed and assessed. PFAS entering Starkweather Creek is a point source. PFAS can remove it from water and then return to the water body. Oops, I went ahead a little bit. So there's from point source, you can have granular activated carbon ion exchange or RO filtration. These are often used at wellheads or I mean, even in a personal home. But you have GAC. Basically, it sucks up the PFAS. You have to worry, you have to be concerned that you're getting all the water, but the PFAS will stick to this filtration, and then you can put the clean water back. Then you have to deal with the contaminated GAC or whatever, but you can do that. And this has been being done, I believe, on like ditch A up near Menominee. So it's not the greatest field method. Also, you can use this thing as foam fractionation. There's a place up near Green Bay that has a landfill, and what they're doing is they're taking the leachate. You take the leachate that's high in PFAS and you make foam. PFAS, like I said, it's a surfactant, it's like soap. So you have a air stone, you bubble it up, it gets concentrated in the foam. So you can concentrate in the foam, you can further concentrate it, and then you remove it. You don't have to deal with the contaminated GAC and stuff and put that in a landfill. But this is another way to deal with it. But also, if you have a diffuse area of groundwater, you can have this in situ remediation where you inject liquid activated carbon injection. And you create basically a curtain in the groundwater, or I'm sorry, in the aquifer. It'll hit that curtain of activated carbon and it doesn't feel, they've been using this, and I've heard several talks about keeping PFAS in sight, on a site, and get it, keep it from flowing downstream and off site. So you can look these up. So there's some good options there if we want to talk about that and discuss that. I'll stop there. I think I went a little over, but feel free to contact me. This is my email and a phone number, and I'll answer some questions. Thanks.
We do have a little under 10 minutes. If anyone does have a question, just feel free to raise your hand and I will trot on over with the microphone.
I'm not too certain I followed the information on the weeds and stuff like in Lake Monona. My question is, do they accumulate PFAS, and when the Dade County cuts the weeds and they go out as compost or mulch, is that dangerous or not?
Yeah, I mean, the PFAS is in the weeds. I mean, I showed that, but the concentration is below the current levels for, biosolids and land spreading and what, we've been using in the States. So I mean, it's detectable but low.
My understanding is that the EPA has to review toxicology once every 6 years. In 2016, they came up with 70 parts per trillion for the two main less and give away. About halfway through that cycle in 2018, DHS dropped the level to about 20 for drinking water, so that's a factor of 3.5. At the beginning of the cycle in May of 2022, the toxicologists at the EPA dropped it by a factor of 10,000 from what it was at 70 parts per trillion. It's hard for me to understand how the current fish advisories could be protective of human health when the EPA has decided to drop the levels so far below what they were in 2019.
Well, the concentrations that you're talking about are drinking water. So that's different than surface water, and that's different than fish concentrations. Because you're drinking water every day, and you're drinking lots of water, you know, let's say liters of water, like a gallon or whatever. The levels in drinking water have to be a lot lower because you're getting exposed to a lot of mass of water and so forth. The concentrations in the fish are from, they've calculated those based on how much you eat. And that's why it's based on like 1 meal per month, 1 meal per week, or do not eat. So it's based on, I believe, on an 8-ounce serving of fish. And they do their calculations from, you know, eating the fish. So that's why there's the disparity. Water needs to be a lot lower because you're eating a lot more. I mean, if the low, you would have to have a lot, like say if you're eating pounds and pounds of fish a day, then you know, if everybody, if you like you need water to live, if you needed fish to live and you're eating like pounds and pounds of fish a day, the water would be, the fish concentration would be lower. Am I making sense? So it's kind of an apples and oranges little thing. It's all about toxicity is based on you know, one of the factors is how you're receiving that contaminated. And usually drinking water concentrations are lower for most contaminants. And then fish is based on, you know, eating and being rid of it.
One of these said it's everywhere. Where does it come from?
Good question. I don't know a specific product that you could hang your hat on. I haven't delved into the PFAS question as much. It's not one of the compounds I'm strong on, sorry. I think that's what, I better not speculate.
Back to the second.
Yeah, I mean, a lot of these are, yeah, used in several different products and so forth. You know, I'm not sure what the mixture is for that industrial application specifically for PFAS. Sorry.
Patrick, we have a question online, which
Sure.
is, has the use of PFAS been eliminated at the airport? And has the source of new PFAS been eliminated? And if so, where is the legacy PFAS coming from to the West Branch of Starkweather Creek?
They've eliminated the use of PFAS in most firefighting situations. Even the DNR had a collection program where they were taking back from fire departments PFAS containing AFFF. And they're, I believe, I'm pretty sure it's similar for the for Truax as well. This is historical contamination in the soil and groundwater. And it's just been continually, they used it a lot. My understanding is, I mean, when you do the training with the firefighting foam, you go out, it was common for a lot of airports to have a burn pit. So you set something on fire and you practice putting it out. And then the next guy comes in line or gal, set something on fire and put it out. And you keep doing that over decades. And you know, I remember in one job I had, we had fire extinguisher training once a year. I'm not sure, you know, how often people did the training. These were also larger fire trucks and so forth. So there's a fair amount residual there to deal with. And it's not common. I mean, there's other, like I said, that we've seen this Fort McCoy, there's other airports as well around the nation. But Mitchell, I didn't talk about Mitchell Field, I should mention, also has high PFAS that's in the data.
Thank you so much. Really, really interested in your ideas about how our lakes can be cleared out eventually. And, if you could talk a little bit more about that issue. I know that, when we're talking about phosphorus, we have legacy phosphorus talk about, sucking them up in the creeks on, going into Mendota. And I think about, okay, the sources from the AFFF, fire training, next to Starkweather in a couple places. And, talking about the sediment, I thought you said PFOS sticks to the sediment more, so could you talk a little bit more about what your thoughts are on kind of that whole system and what it would really take to clear that out? You mentioned it a little bit, but maybe go over that, thanks.
I don't have I was just throwing out a talking points discussion. I think the main thing is that, with a lot of these things, it's kind of like, okay, first, we have a problem, admitting we have a problem. And we, can we talk about things? I'm not as involved. I know that there are meetings with, the mayor, Dane County, the Air Force, and it's a complicated situation at the airport. But these are some applications that I threw out there that could potentially be used. We'd have to get with engineers and scientists, and the main thing, and if I haven't mentioned it, it's like, once the genie's out of the bottle, it's hard to put it back. And I think we've shown that it's, going all the way down the Yahara River and so forth. If we can keep it defined to the airport, or if we can remediate it off the airport, that would be a good place to start. I know it's not cheap. If you want to get into that discussion, I don't know about airports and so forth, but I know right now there's infrastructure funding and there's available funds for PFAS remediation. A lot of communities are putting in filtrations for the drinking water wells and so forth. So there's federal funding potentially that could be sought or gone after. So it's a complicated situation, but like I said, if we can either keep it there or remediate it and so forth, but like as I said, once we clear it up from Starkweather, I think we'll see benefits fairly, soon, which is kind of encouraging. Within our, my lifetime, we might be able to benefit that, and this is something that's right out our back door. So.
Wonderful, Patrick, thank you. We're just over 9 o'clock, so we want to be respectful of the time. Thank you so much. I know there are a few more hands up, and if there were any questions online, please feel free to shoot us an email, info@cleanlakesalliance.org. We'll get you connected either to Patrick or whoever might be able to help answer your question. This entire presentation will be available on the Clean Lakes Alliance website and on the YouTube channel tomorrow morning. So if you want to rewatch or share any of this information, that will be available. Our next meeting will be Wednesday, September 25th, right back here at the Edgewater. We have a special presentation on the recently approved master plan for the Lake Monona waterfront redesign. It's beautiful. I'm excited about this one. The Sasaki staff will be sharing the water quality improvement aspects of their plan, including stormwater treatment along John Olin Causeway. Of course, all Clean Lakes Alliance donors and sponsors are able to attend this event regardless of DMI member status. We hope that you are able to join us. Again, I will be there, and it'll be really exciting to hear more about the improvement aspects of that. Thank you all for joining us this morning, and have a great day.